I have a certain combination of materials, powder, polymer. Firstly, I need to know how much to mix. How much powder can I put in a mixture and still get uniform mixing? The second thing is, how much shear rate do I need to provide to make sure that agglomerates are broken down, right? Sometimes the shear rate is not enough. You can uniformly distribute the agglomerates without breaking them, and that's a problem. We don't want that, right? So can we have a way to tell how much shear rate to apply for a given concentration of powder or for a particular type of polymer, right? So that we know beforehand, right? Rather than take the material out of the mixer and then say, okay, no, it's not mixed and put it back in, or change the amount of powder, right? So you have agglomerates, they need to break down. That's what the model has to be capturing. You have different particle sizes, right? And so smaller particles, higher surface area, they might agglomerate more, right? More particles, more of them clustered together, they might need a higher shear rate. And then, of course, you change the polymer by changing the viscosity, right? So on the one hand, you have a cohesive force, that is something that's holding particles together. On the other hand, you're applying a shear force through the fluid, referred to as a hydrodynamic force. Whereas you're applying a shear force, the liquid is transmitting the force and acting on the agglomerate and breaking it apart, right? If this force that you're applying to with the mixer is greater than the forces holding the particles together, then you're going to break down agglomerates, you're going to achieve homogeneity, right? So in soil mechanics, right, so in civil engineering, people have looked at how those agglomerates are put together as a function of these parameters: particle size, okay, and then how much particles, volume fraction of particles, right, and then some kind of a cohesion constant, right? But mainly, what does this say in terms of, as you reduce the particle size, what happens to the cohesive force? Yeah, it goes up, right? And so now it captures one aspect, that small particles are more difficult to make homogeneous. And so the model captures that. It also captures the fact that you have higher volume fraction, it's more difficult to break up the cluster, right? So that's one thing. The other thing is now how much shear rate to apply, okay, which is gamma dot, the shear rate. Right? And so accordingly, what is the force, the hydrodynamic force? By increasing the shear rate. If you have too high a shear rate, you're going to wear and tear the machine. The machine is going to get worn out more easily, right? So you don't want to have too high a shear rate and have then contaminants. On the other hand, and also you're using more energy, so manufacturing cost is going to go up, right? So it depends on the viscosity. The higher the viscosity, it turns out, the more easily the force can get transmitted at any given shear rate. And it depends, of course, larger clusters are going to require a higher force to break down, right? So if you balance those two equations, right, basically you'll get a specific critical shear rate, right, where those two forces are equal. And so now you get a relationship on particle effects, solid volume fraction effects, and viscosity and polymer effects. If the binder viscosity is higher, the force gets transmitted better, okay? But if the higher the viscosity, you need a higher shear rate, so they're interrelated to each other, okay? Yes, but the thing is, for the force that is applied by the machine to be transmitted through the liquid onto the cluster, the higher the viscosity, the greater the machine force, the greater the conversion of the machine force into force that acts on the particle to break it apart. Okay, so they're competing requirements. Right? This is so there is you need a high viscosity to break down clusters, but a lower viscosity will allow to distribute the particles more evenly. Okay. In this case, all you are required looking at is how much shear should I apply for a given powder, polymer, and concentration combination, mixture right? What is A, what is B? If I change those two, and if I change the ratio of A and B, how much shear rate should I apply? Right? So at this point, you have a design equation, right? You need to apply a certain minimal shear rate, and smaller particle sizes will require a higher minimal shear rate, and more concentration will require a higher shear rate. Right? So there's like now a sort of a starting point of a design equation that allows you to answer the question, what machine setting should I have? Today, I mixed stainless steel particles of 50 microns in polyethylene. Tomorrow, I'm mixing 100 nanometer zirconia particles in polyethylene glycol in water, right? And I've changed 65 volume percent of stainless steel to 53% of zirconia, right? How do I change my machine settings? This is one way to be able to do that, right? And so in practice, right, what is the meaning of that equation, right? This is how shear rate changes as a function of phi for different particle sizes. Right? So as you increase particle size, what is happening to the critical shear rate? Right? As you're increasing the particle size, the minimum shear rate to break an agglomerate goes down. Right? As you add more particles, shear rate goes up, and it goes up more dramatically for particle size compared to solid surrounding, right? So it's consistent with the general idea that more concentrated powder polymer mixtures are more difficult to mix, and smaller particle sizes are more difficult to mix. This allows some kind of a quantitative manner to try to see how much more difficult is it. How will you adjust the choice of mixer or the mixing speed to break down clusters? And so in practice, binder of about 10 Pascal seconds viscosity, about a 20 micron powder, you increase the solids loading, the mixing torque increased, the torque variation also increased. We said that if the torque is higher or the torque variation is higher, there are going to be more agglomerates, right? In this case, we were doing the mixing at a shear rate that was lower than the critical shear rate. This was a critical shear rate from putting these terms into that equation, and this was the actual shear rate. At lower concentration, the model predicts that your critical shear rate is about 80 and you're applying 95. So you have lesser mixing torque variation, better homogeneity. Okay. So comparison between experiment and theory. Things like that are used even for mixing two different polymers. Right? There is something called a capillary number, which is same thing. It's a ratio between this hydrodynamic force, right, which is the applied shear stress times the radius of the droplet. So you have your melting polymers and you're dispersing one polymer in another polymer. Right? And there's a surface tension that wants the droplet to remain by itself instead of dispersing into the next polymer as a liquid, because you're dealing with two liquids, right? So surface tension is just like a cluster term. There's something holding the polymer together, one polymer, and there is an applied shear stress that wants to disperse the polymer in the second polymer phase. This is the case of blending two different polymers. We said that in in powder processing, we sometimes use combination of polymers, right? Low viscosity polymers combined with high viscosity polymers. How do they blend? Right? Again, this is the kind of similar idea. You need enough shear to overcome surface tension of the droplet, and then you can disperse the material. Right? So that is as far as some ideas behind, depending on what you mix, answering the question of how much to mix and what shear rate to mix at. Right? And depending upon that answer, you can go to different types of mixer types and change the, and depending upon the geometry, you can adjust the shear rate. Right? And so a mechanical engineer does all of that. Now the question is, okay, you mix two things and they are relatively homogeneous. What properties can you measure that are sensitive to changes in these properties? So you can, changes in the mixture homogeneity, changes in the mixture concentration of powders and so on. Right? And which of those are then of importance to processing? Right? So let's say you have alumina in this type of a polymer combination. You have an ethylene propylene copolymer. You have another graphed copolymer of propylene and maleic anhydride. Right? We said graphed polymers, one part binds to the powder surface, the other part combines with the polymer, and so you can have better strength or better uniformity in mixture. Stearic acid and paraffin waxes are lower molecular weight materials, and so you can say that they are used to control the rheology. Right? In this case also, in both cases you had equivalent amount of powder. In the case of the commercial material, it's polyacetal, which is another polymer primarily. It has a little bit of polyethylene in it. So what we are trying to do now is compare for these two materials, what are the different mixture properties. First one is rheology. So viscosity as a function of shear rate at different temperatures. Right? So for instance, at about a shear rate of about 10 power 3, right, 1,000 reciprocal seconds, the viscosity is about 100 for the wax polymer mixture. In the case of the commercial polyacetal mixture, it's about, say, about 300 or 400 Pascal seconds, so slightly more viscous. In all cases, as you reduce the shear, as you increase the shear rate, viscosity goes down. Right? This one seems to have a yield stress, right? There's some region where at some point viscosity is relatively constant at low shear rates. Also, as you increase the temperature, the viscosity decreases. Right? Orange is the lowest, blue is the highest. Right? The temperature sensitivity to viscosity is a little bit lower for these systems, but overall, you get an idea. So, how does viscosity change as a function of shear rate and temperature? Right? That's the question. And this particular model, which is called the cross model, allows you to capture how viscosity changes as a function of shear rate and temperature. And there are a bunch of fitting constants that depend upon the material composition. Right? So viscosity we know changes as a function of shear rate and temperature. This equation allows you to capture the shear rate effect, and this allows the temperature effect. Right? It's just a way to fit the data, and it's called the modified cross flow model.